13.4 billion years. That is how far back in time the James Webb Space Telescope has seen. A galaxy called JWST Z14-0, formed just 290 million years after the Big Bang, when the entire universe was barely 2% of its current age. Webb photographed it, measured its light, confirmed its distance, a smudge of ancient starlight from the edge of observable reality, captured in crisp infrared detail. And yet, 4 light years away, orbiting the closest sun-like star to Earth, there may be a planet. A gas giant roughly the mass of Saturn sitting inside the habitable zone, the nearest possible world to our own. And it took us until February of 2026 to find the first strong evidence it even exists, after decades of searching, after pointing every major telescope on Earth and in space at that star, after hundreds of papers, thousands of observing hours, and millions of dollars spent. We can see a galaxy from the dawn of time, over 13 billion light years distant. But we struggled for 30 years to confirm a single planet 4 light years away. That is not a contradiction. It is one of the most counterintuitive truths in all of astronomy. And once you understand why, you will never look at a telescope the same way again. Before we go further, if this kind of content is what you came here for, deep verified science explained in a way that actually sticks. Subscribe and turn on notifications. Every video on this channel is built on peer-reviewed research and official data. No guesswork, no filler. Let us begin with what seems obvious. If a telescope can see something 13 billion light years away, surely it can see something 4 light years away with ridiculous ease. Distance should be the only variable that matters. Closer means easier. Right? Wrong. And the reason is one word: contrast. When Webb images a distant galaxy, it is looking at an isolated source of light against the empty blackness of deep space. That galaxy might be faint, unimaginably faint, but there's nothing else nearby drowning it out. It sits alone in the dark. Webb collects its photons over hours, builds up the signal, and the galaxy appears. The challenge is sensitivity, gathering enough light, and Webb was specifically designed for that. Its 6.5-meter gold-coated mirror and infrared detectors are optimized to collect the faintest whispers of ancient light from across the cosmos. But finding a planet around Alpha Centauri A is an entirely different problem. The challenge is not sensitivity, it is contrast. The planet is not sitting alone in the dark. It is sitting right next to one of the brightest stars in the sky, drowning in its glare, 10,000 times fainter than the star it orbits. Imagine trying to spot a firefly hovering 1 centimeter away from a lighthouse beam, from 100 kilometers away, at night. That is approximately the contrast ratio between Alpha Centauri A and a Saturn-mass planet in its habitable zone. No amount of raw light-collecting power solves this problem. You need something else entirely. You need a way to block the star while keeping the planet visible. And that technology, called coronagraphy, is staggeringly difficult to execute at the precision required. Here's how a coronagraph works. Inside the telescope, a tiny physical mask is placed in the optical path at exactly the spot where the star's light focuses. This mask blocks the star's core. In theory, the light from the star is gone and anything faint sitting nearby becomes visible. In practice, stars do not focus to perfect points. Light diffracts around the edges of the telescope's mirror. It supports struts and the mask itself. This creates a complex pattern of residual starlight, speckles and rings that spread across the detector like ripples in a pond. These speckles can be thousands of times brighter than the planet you are trying to detect, and they shift as the telescope flexes, as temperatures change, as the star moves slightly in the field of view. The planet hides inside this chaos. Separating it from the speckle pattern requires not just hardware, but sophisticated data processing, subtracting modeled speckle patterns, combining multiple observations, running statistical tests to determine whether a faint dot is real or residual noise. And there's another limitation. Every coronagraph has what is called an inner working angle. That is the closest angular distance from the star where the mask can still block light effectively, while leaving the surrounding area clean enough to detect a companion. Anything inside that angle is invisible, no matter how powerful the telescope. For Webb's mid-infrared instrument, the inner working angle for the coronagraphic mode used on Alpha Centauri A is approximately 0.5 to 1 arc-second, depending on wavelength. A Saturn-mass planet orbiting at 1 to 2 astronomical units at Alpha Centauri's distance of 4.37 light-years corresponds to an angular separation of roughly 0.5 to 1 arc-second. That means the planet lives right at the edge of what is physically detectable, sometimes inside the mask, sometimes just barely outside. Depending on where in its orbit it happens to be when you observe. Now compare this to imaging a distant galaxy. JD's GS ZAS-14-0 sits alone. No nearby star is flooding the field with overwhelming glare. No coronagraph is needed. No speckle subtraction. No inner working angle constraint. The only challenge is collecting enough photons from an extremely faint source, and Webb solves that simply by staring at the same patch of sky for dozens of hours, letting photons accumulate on its detectors until the signal rises above the noise. The distant galaxy is easier to detect, not despite its distance, but in a sense because of it. Distance makes it faint, but isolation makes it clean. The nearby planet is brighter in absolute terms, but buried alive under the glare of its parent star. This is the fundamental paradox. Telescopes are not distance machines. They are contrast machines. And the contrast problem for nearby exoplanets is orders of magnitude harder than the sensitivity problem for distant galaxies. Let me make this concrete with numbers. Alpha Centauri A has an apparent magnitude of roughly 0. It is the third brightest star visible from Earth's surface. It floods detectors with photons. A Saturn-mass planet in its habitable zone would be approximately 10,000 times fainter in the mid-infrared and perhaps 100 million times fainter in visible light. Separating those two signals at an angular distance of less than 1 arcsecond is like trying to read a handwritten note taped to the surface of a searchlight from across a city. By contrast, JWST has no searchlight. It is the note floating alone in darkness. Faint, but unobstructed. Clean. There is a second layer to this paradox that makes Alpha Centauri specifically brutal. It is not a single star, it is a binary system. Alpha Centauri A and Alpha Centauri B orbit each other with a period of approximately 79.9 years, at separations ranging from 11 to 36 astronomical units. That means when you point Webb at Alpha Centauri A, the light from Alpha Centauri B is also flooding your detector from nearby, adding a second layer of contamination. The research team that detected the planet candidate in 2026, led by Charles Beischmann at the Jet Propulsion Laboratory and Aniket Sanghi at Caltech, had to develop an entirely custom observing sequence for Webb. The telescope was never designed for this. It was built to find the faintest, most distant objects in the universe. Pointing it at one of the brightest stars in the sky required the Space Telescope Science Institute to invent new procedures from scratch. They observed Alpha Centauri A with the MIRI coronagraph in August 2024. They detected a faint source, a blob of infrared light approximately 10,000 times dimmer than the star, at a separation consistent with 1 to 2 astronomical units. Then they observed again in February and April 2025. Both times, the source was gone, not because it was fake, but because orbital mechanics had carried it too close to the star, inside the coronagraph's inner working angle, hidden behind the mask. The planet was real. But it was playing hide and seek at the very boundary of what the most powerful telescope in existence could resolve. Now here is the part that most explanations of this discovery leave out. Why did it take until 2026 to even attempt this? Alpha Centauri has been the target of planet searches since the 1990s. Ground-based telescopes using radial velocity techniques, which detect the subtle wobble a planet induces in its star, searched for decades. The European Southern Observatory's high-accuracy radial velocity planet searcher, installed on the 3.6-meter telescope in Chile in 2003, observed Alpha Centauri extensively. In 2012, a team announced the detection of an Earth-mass planet orbiting Alpha Centauri B with a period of 3.24 days. The discovery made global headlines. It was published in Nature, and within 2 years, it was retracted. The signal turned out to be an artifact of the data processing, a ghost in the noise. That failure haunted the field. It demonstrated that Alpha Centauri, despite being the closest system, was also one of the most treacherous to study. The two bright stars contaminate each other's spectra. Their orbital motion shifts absorption lines in complex ways. False signals lurk everywhere. Direct imaging with a coronagraph bypasses the radial velocity problem entirely. Instead of looking for an indirect wobble, you photograph the planet itself. But until Webb, no space telescope had a mid-infrared coronagraph sensitive enough to attempt it on such a bright, nearby target. Hubble observed invisible and near-infrared but lacked the contrast. Ground-based telescopes with adaptive optics achieved impressive coronagraphy, but atmospheric turbulence limited them at Alpha Centauri's angular scales. Webb changed the equation. MIRI operates at wavelengths between 5 and 28 micrometers, where a warm planet emits more of its own thermal radiation relative to its cooler host star. At 15 micrometers, the planet-to-star contrast ratio improves by roughly a factor of 100 compared to near-infrared. Combine that with the stability of space, no atmosphere, no turbulence, and for the first time in history, the observation became physically possible. It still required custom engineering, it still required heroic data processing, and it still produced a result that appeared and then vanished. But it worked. As of May 2026, astronomers have confirmed 6,286 exoplanets across our galaxy. Nearly all of them were detected indirectly, through transits or radial velocity measurements. Almost none have been directly imaged, and of those that have, virtually all orbit far from their stars, at separations of tens or hundreds of astronomical units, where the contrast problem is manageable. The Alpha Centauri candidate, if confirmed, would be the closest directly imaged exoplanet ever, at a separation of approximately 1 to 2 astronomical units, around a sun-like star, in the habitable zone, 4.37 light-years from Earth. And it took the most expensive, most powerful, most technologically advanced observatory ever built by humanity, operating at the extreme limit of its design capabilities, using a custom observing sequence never attempted before, processing data through millions of simulated orbit models, to produce a tentative detection that appeared once and then hid. Meanwhile, that same telescope photographed a galaxy from 290 million years after the Big Bang as part of a routine survey. No special procedures, no custom engineering. Just point, stare, and collect photons. There is a lesson in this that goes beyond astronomy. We assume that nearness equals accessibility, that if something is close, it must be easy to reach, easy to study, easy to understand. We apply this intuition constantly. The nearest star should be the best studied star. The closest planet should be the first one found. But the universe does not obey human intuition about convenience. The challenges of observation are not determined by distance alone. They are determined by contrast, by geometry, by the specific physics of light, by the limitations of the instruments we build. Sometimes, the most distant object in the observable universe is easier to photograph than the one next door. That is humbling. It tells us that proximity is not understanding. It tells us that having something close does not mean having it figured out. Alpha Centauri has been visible to every human civilization that ever existed in the southern hemisphere. Navigators used it. Poets wrote about it. And until 6 months ago, we had never confirmed whether a planet orbited its primary star. What happens next matters enormously. The research team will request additional Webb time to observe Alpha Centauri A when the planet's projected orbit places it outside the inner working angle again. They need at least one more confirmed detection to elevate it from strong candidate to confirmed planet. And the Nancy Grace Roman Space Telescope, launching on August 30th of this year, carries a dedicated coronagraph instrument designed specifically for directly imaging planets around nearby stars in visible light. Roman's coronagraph will achieve contrast ratios of approximately 100 million to 10 times better than any previous space coronagraph. If the Alpha Centauri planet is real, Roman should be able to see it and measure its reflected light. And begin characterizing its atmosphere. We may be months away from confirming the closest exoplanet to Earth ever directly seen, a planet in the habitable zone, around a star you can find in the night sky without a telescope. And the reason it took us this long is not that we lack ambition or funding or intelligence. It is that the universe placed the hardest observation problem in astronomy right on our doorstep, and then put the easiest ones 13 billion light years away. That is the truth behind this paradox. We can see the edge of time. We cannot easily see across the street, and both of those facts are consequences of the same physics of light. If that reframed how you think about telescopes, about distance, about what it means to observe, let me know in the comments. What surprised you most? The fact that Webb needed custom engineering for the nearest star, or that a galaxy from the dawn of time is technically an easier target? Subscribe if you want more of this. Share it with someone who assumes closer means simpler. And turn on notifications. The next video is already coming. Thank you for watching. I will see you in the next one.